Okay. So I hope everybody's hearing me. It's okay? Yeah? So first of all, I'm very pleased to be here. You can't know how much I'm very happy to be here and how much in France we're quite impressed by the level of, in general, of the Russian universities in the domains of mathematics. And especially this one in the sense that we have a lot of cooperations with some of your colleagues. And basically, this is a unique opportunity. When I was asked to come here, I was extremely happy. And I said I cannot avoid coming here and at least see the place. So my talk is going to be about AI. Of course, you can ask me any question you want. And basically I can give you many ideas on what we're doing afterwards during the tea break. So as far as I'm concerned, my name is Merouane Debbah, and I'm leading basically the mathematics lab of Huawei, where we have more than 150 researchers working on various topics related to mathematics in Paris. But overall, we have a lot of researchers working on the fundamentals of mathematics related to many problems. So the first question that you should ask yourself, many of you are undergraduate, graduate students, they are at the stage of trying to go into a field and a career and asking themselves where I should go. And the best way is to give you an anecdote about why I decided to go into the field of telecommunication when I was a student like you in 1998. So in 1998, you have to know, that was more than 21 years ago, very far away, when basically you were making a call, you had to pay for the call, which is basically a bit different because here you have unlimited calls. And you have to know that at that time, I had a nice girlfriend, and basically, whenever I used to call her, I called her and hung the phone, okay? And why I did that? Because it was just to say, I'm thinking of you, or I'm arriving, and by calling and hanging the phone, you're able to send one bit of information. I don't know if it's clear for everybody, and you don't pay for it. It's great, because basically you can send information without paying. So in 1998, I said to myself, this is a great system because I can interact with people by just sending information, by ringing the phone and hanging the phone. And so in 1998, I said to myself, I was doing physics and mathematics, well, maybe I should do a startup building basically a protocol on ringing tones without paying. What it means, an A would be one ring, a B would be 2 rings, a C would be 3 rings, and then I hang and then I go on like this by just ringing tones and sending. Of course, you build an interface for that, and of course, as usual, you have a problem with that because it's latency. Okay, it takes time before you can transmit a message. But there's a lot of cases where you are what we call delay insensitive. Sending a fax, for example. At that time in 1998, sending a fax to Africa was extremely expensive. It would cost you 8 euros per page to send it from Paris to any town in Africa. And I said to myself, I could start building a whole system where people could basically transmit information by exploiting an existing network. I would be the Uber of the taxis where you have a given system. So of course, that was my first trial in getting into telecommunication. I was extremely happy. And by doing that, of course, you don't do it in a blunt manner. You start studying, and you start studying a field called information theory. Because basically, you don't encode an A with 1 ring, a B with 1 ring, and a C with 2 rings. You look at the most probable letters that come in, and those are the ones which you map to the ringing tones, and so E is more probable, for example, than X, so this is where you're going to do the least ringing with respect to the others. So I started building the whole thing, and of course, when I decided to make my startup, I started looking for investors, and the operators came to me and said, okay, you are very smart, you're trying to disrupt the system, because you're trying to use our system to make free calls. In fact, we thought of people like you, and when we built the system, we decided to desynchronize the transmitter from the receiver. What it means that in actual system, we cannot guarantee you, and they made it on purpose, that the amount of ringing tones of the transmitter is the same as the receiver, to avoid people, like me, to exploit the system. Why I'm giving you this anecdote? Because basically I wanted to get into deep details in understanding how it works. And this is why I decided to go in real companies to understand the thing, and really to understand how it works to avoid these problems. Of course, Another good part of research is that the idea that I had in 1998 turned out to be very useful when I joined Huawei in 2014, 2015, 2016, because the exact idea that I had before had an applications 20 years later, and the application is called IoT, Internet of Things. You're interested in low data rate. You're not interested in high data rate. So there's many applications of low data rate where your washing machine says, I'm on, I'm off, and you only need to send 1 bit. And these kind of systems, by the way, we're using them now, okay? This was just an anecdote to give you why you would join a company, because basically you have a problem and you're matching that problem to the right company, and I hope our company is the right one, where you can develop your expertise and solve those problems, which are long-standing problems. Okay, let's go now to the talk. I'll jump rapidly on these slides because my colleagues have been showing you why Huawei is a nice place. But to summarize what my colleagues said, I would say that one of the big things of Huawei is 2 things. The first thing is that we control the chain from end to end, meaning that you have a plethora of places where you can play the device, the network, the cloud, the enterprise, and basically you nearly have any place where you can play. Second thing is that it's a high-tech company. What it means, a high-tech company? It means that half of our employees are doing R&D. You have to know that this is unique. In the classical industry, it's 15% to 20% maximum people doing R&D. It means that when you come in our company, there's 1 chance over 2 that you'll encounter people speaking the same language as you. It's not a marketing guy, it's really a technical guy. You can write equations with him. You can talk about equations. You can talk about technical things. And I think if you got those 2 messages, those are the most important thing. Let's start now with a talk on AI. So since I didn't know your background, I'm going to be starting in a very nice manner and small, step by step. So here you have 2 pictures. One here is a famous guy called Newton. Okay? And one of the good things about Newton is that he developed, among other things, the Newton equation. So why is the Newton equation very nice? Because at high school, we give you this exercise. And this exercise at high school is about what we call a ballistic kick. It means that we tell you with which angle you have to kick the ball for a given distance. Okay? So if you know Newton, no problem, you compute that equation, and then you can find the angle with which you have to kick the ball. Clear for everybody? Now, in our business, there are many cases where we don't have access to this guy. Why? Because we need to wait many years before the theory is developed. And second, also, things are highly complex. They depend on too many parameters, and we cannot understand how things work exactly, meaning we're not able to relate the equations which govern. In telecommunication, it's basically end-to-end communication. There's many things in between your network which makes it difficult to be able to optimize it in a neat manner. So if you don't have this, and the military, by the way, know exactly this example, what you do is you kick like hell. You kick the ball like hell. And then you write a database where on one column you have distance and the other column you have angle. Clear for everybody? So next time, of course, your boss asks you to kick at a given distance, and he asks you to kick at 450 meters, you're going to look at the database if 450 meters is there. This is called data mining. It's known since for years, but you need still to be smart. Smart in the sense that you need to not do a search 1 by 1, but clusterize your data. 450 is in the class of 400, 500. So you'll go there, and on 2 or 3 steps, you're able to get that number. Now, where people would talk about intelligence, in fact, it's just a regression. If the distance is not there, no problem. You will do some kind of regression of the distances and find what is the regression that you have to do in the angle domain to find exactly with which angle you kick the ball. So of course, in the language of, let's say, AI, machine learning, and all the others, what you do is you train a black box where the input parameter is distance, the output parameter is angle with all the database. And next time you have a new distance to input, you get the angle. So it's quite magic because today, instead of using Newton equations, we can use all the data generated by Newton to solve the problem. From a scientific point of view, I totally agree with you. There is a caveat because why would you do this when you have it? No reason. But why would you do this when you don't have it? This is another question. That's the first thing. Second is, and I'll talk about it, is of course, modeling is compression. So of course, as a scientist, the first thing you would do is compression. okay, to compress the data. Because with one model, you can represent things. Same thing for Maxwell. We'll talk about it, why we don't do these techniques anymore, but we will need in the future to do them for a simple reason, because we have a lack of energy storage capability to do these techniques. And this is why we need you guys to solve those problems. Let me go back to this problem. By the way, this example that I give you is something that we implement in our system. It's called AI-based MIMO beamforming in 5G. In 5G, the base station beams towards the users, and we have beams, position, beam, position, beam, position. Next time you're in a new position, our neural network is able to discover, well, is the new beam by interpolating with all the previous positions. Clear for everybody? This is something that is implemented. What is the caveat of this technique? And with that you have understood, is that when you have trained your neural network when it's sunny, excuse me? Overfitting. Can you repeat your...
You might have overlaid the model so that it will give the right results on the training data.
Yes.
But not the right results on other data.
Yeah, so this is exactly what are the problems, and this is what we need to solve. The first problem is that you trained with the data or a basis of data when it's sunny. The day you have to do your experiment, it's windy. Clear for everybody? So there's a lag because you need to train for any new configuration. This is too costly, we know it. We have techniques related to AI which are still able to do some things if the two databases are correlated. It's called transfer learning. If you learned when it was sunny, you could still exploit that learning when it's windy, basically, by doing this transfer, which is exactly an experience that you have, is that if you learn English, it's much easier for you to learn German. Nacht. You go faster. And we know, for example, for kids, it's very important when you have kids to put them doing music, because music is some kind of universal basis language, and then they have a great capability of learning languages faster. So these things, we use them, but still we have a caveat, because some cases, well, we are stuck to retrain every time. So it has a cost to retrain every time, okay? Telecommunication example, very easy. We deploy a network in St. Petersburg. We optimize all the parameters of St. Petersburg based on the data. Our base station knows how to beamform. We then transfer the weights of that neural network to Moscow. And instead of starting randomly to initialize our neural network that deploys the network in Moscow, we start with initialization parameters of St. Petersburg. Why? Because the behavior of people in St. Petersburg is not so far from the way they behave in St. Petersburg, for example. Third, also problem that I talked that is something extremely complicated, and this is the work of data scientists, is that in this example that I'm giving you, I told you there's a one-to-one link between angle and distance. In fact, this is wrong. You need to know also what we call the initial speed, okay? And this is a big problem because basically you need to know, or at least have a hint on what are the input-output parameters of your black box. It's not immediate. Here it's because you have experience. It is as if now you decide to work in a health company and they tell you, you're a smart guy, you have all the data of the patients. Can you find from the temperature the ones who have a cancer? No, because you feel that you need more. But then you don't know what you need more. You need maybe a column of blood pressure. You add it. It doesn't work. And then you start adding. So today the work of a data scientist is a lot of tuning, and we cannot continue like this because you start working on the input-output and trying to have some kind of hint of what's happening. The last point, which is extremely complicated for us, is that we are not able today to create some sophisticated algorithms which can extract the rules which are, let's say, governing this thing. What I mean by that is that you learn to kick on Earth. How do you kick on the moon? It's a generalization. So you need basically to find new algorithms which are able to basically find some kind of invariance related to that data. Gravity, for example, is an invariant, and in which you can build something. Today, we have a hard time. Many mathematicians are working on topology, geometrical structures, stuff like this, to try to find some invariant. For example, in image processing, we know that an image is invariant by translation, rotation. So we have some invariants and we can build some kind of nice techniques. But if I give you a complete set of data that you don't have any clue, finding those invariants requires some more sophisticated mathematical tools. Today, the approach people are taking is, instead of doing classification-based techniques, correlation-based techniques, this is what we're doing, to go more towards the techniques of topology and geometry, for which we have no clue. Now, why this technique became famous? It's because of the people doing speech recognition. You have to know that if you were in the 80s, at least your professors were in the 80s, a lot of people tried to do speech recognition by modeling what we call the larynx here, and trying to model this as a filter, and trying to find how you can recover basically some kind of filter design of the emission of the sound. It never worked. It worked the day we decided to stop modeling and consider speech recognition as a classification problem. It's a classification problem. What it means we take a lot of data, we take a lot of patterns, and next time we have a new one, we try to relate it to which class it is, and once it's done, we try to make some correlation to find what it means, okay? And that was a big hit in terms of success. I'm not saying that this is the approach to do in every field, but it turns out that in speech recognition, this is something that works quite nicely. The last point that I want to mention before getting into my business is basically the role of data. And the role of data is instrumental and is basically the most problematic issue we have in a company. Even in my company, I'm working in it, getting the data is a huge process. Not because they don't want to deliver it, because we need a documentation of all the processes, how the data is generated, otherwise we take wrong conclusions. So this is a very famous example, and this is a plane, and this is the plane which was going back to England after doing some bombarding in Europe. Okay, and these are the kinds of planes. And the red dots are the shots that the plane was having. Clear for everybody? And so the commander of the base in England said to the statisticians, at that time the data scientists were called statisticians, and they asked them, hey guys, tell me where we should reinforce the plane, where we should put more metal to reinforce to avoid that the plane gets down. And of course, the statisticians came up with some very sophisticated algorithms saying how much, I would say, metal they should put on each point, depending, of course, on these bullets that they had and all the data. And of course, then came the pilots. And the pilots said, no, in fact, your conclusions are totally wrong. You should reinforce the plane where there is no dot, no red dot. Why? Well, because basically, the planes which were shot here never came back. So we had missing data. Am I clear for everybody? So in fact, we were taking conclusions on the data set without the knowledge that many planes, which in fact were shot exactly on those points, they never came back. The pilots, of course, knew the field because they were experts. They were seeing that their colleagues were not coming back. And this is exactly the type of problems we have in our discipline, is that basically you need also to know the whole process where the data came in and how the things went in. Now, if you understood this, now we can start, and I think you got a global picture of what you want to do. Okay, in my talk I'll be mixing, but if I was giving a more scientific talk step by step, I would not do it. But here I'll be mixing AI, machine learning, deep neural network, because we don't have time, and in general, we like the word intelligence to put it everywhere. But there's a clear distinction between the three of them. There's also a clear distinction in the way you learn based on things we call unsupervised learning, supervised learning, and reinforcement learning. The most, I would say, famous techniques are based on supervised learning, but you have to know that we cannot continue anymore like that, because you need people who are capable of labeling the data. And that's what you do in general when you log on a system. They ask you to, by clicking on the pictures, to label the data, okay? And by the way, this is something that is bad because today we need a lot of labelers. You have to know, for example, in Finland, some startups use prisoners to label data. A cat, a non-cat. They come in the morning and that's what they do. We cannot continue doing that. We need more of you guys to push towards the techniques of learning without a teacher. Okay? It's like as if you are playing football. By playing football, you can either have a teacher who tells you how to kick, or I give you a ball, and you can kick the ball on the wall and start learning how to improve by getting some kind of reward every time you kick the ball. So this is like systems which we implement related to reinforcement learning, for example, okay? Now, neural networks have been extremely, and what we call artificial networks have been extremely famous thanks to a very nice theorem called the universal approximation theorem. There's a structure which has been built since the 90s based on these layers and neurons, on which everybody became very happy because of this famous theorem that tells you that you can nearly approximate any function up to some conditions thanks to the structure that we have in neural network. So this is what kicked in the discipline, because you need to approximate a function, Newton, no problem, you can approximate it. You will not understand it, who cares, but you can approximate that function by a structure which is the structure based on neural networks. So it's a very strong theorem, and this is one of the reasons also many people uses it. And at the end, everybody's playing with the structure because you have some kind of universal approximator of the kind of function you're trying to find. So this is extremely nice for the people, although, same thing, we don't understand what's behind. We just have an approximation of a function we would like to build. Okay, I'll jump on these things. I think there's a lot of interest for you. You have to know the last step before I continue. There is very few, and our company is not happy about it, there's very few people who understand what they're doing. Why? Because there's a tendency today of having software available on the web, and especially TensorFlow and others, where as a data scientist today, you don't need to re-implement everything, but you need just to tune the parameters. It's like Simulink. If you have MATLAB, you just tune the stuff without really understanding and coding. This is very bad. I'll give you an example. 1 year ago, because of my communication case, I had to build up a complex neural network. And I thought my engineers were using complex numbers. And I told them, okay, you did the result. The result is not so good. I'm quite surprised that it's not so good. I told them, can you explain me? They told me we've been using TensorFlow, but I told them TensorFlow is for real numbers. And they told me, yeah, but complex, we just stacked the vector and did it that way. But I told them, why did you stack? You could have mixed things differently. And they told me, oh yeah, you're right. And oh, okay, then maybe we have to do a complex neural networks with complex numbers. And then we start building the complex neural networks, and then you get some very good results where you're able to rediscover something like the FFT. You will never be able to rediscover the FFT for a transmission scheme based on the actual systems. So you need basically to dig in, be careful. If you start using only the software, if you're in that case, that's good for you. Okay. Let's go now in the AI in industry before I start with my cases. So you have to know that AI is not new, although everybody's talking about it only today, but it started in the 50s with people that you know, called Turing, Shannon, McCarthy. Many very famous people gathered around that, and there was a huge progress. And then we came into winter. After the first winter, in the 80s, we started with something called expert systems. Many of your professors have been working on these expert systems, and then it got back. And then a winter came in. And now today we are seeing a progress which is phenomenal, and I'll explain why the reasons. Many people think that the winter is going to be happening also, for a couple of reasons. The first reason is energy. Today, the amount of resources which is used to get the results of AI is getting incredibly large. And it's basically, by the way, all the technologies that we're building today. Take, for example, blockchains. Today, mining Bitcoins is great, but the total amount of energy to mine a Bitcoin per day is equivalent to what Ireland consumes per day. It just gives you the numbers. Today, the same thing, the computing energy that is required for AI is getting too much. And we fear, and that's a bit normal, when you think of why would scientists, instead of using Maxwell equations, start doing neural networks for doing propagation. There are some people trying to do that today. It doesn't make sense. But still, it means that we have the computing power, okay? Of course, you see it also by the number of publications which are rising. Now, one good thing also that when you look back at history, there's a famous paper of Shannon, but it's nearly at the same time with, I take here Shannon, but you could take also Kolmogorov here and others, but they all came up at the same time. But he came up with a paper called Programming a Computer for Playing Chess. I strongly encourage you to read it, okay? So, of course, Shannon, as you know, wrote two very important papers. One about what we call secrecy of systems, and basically how you built a fully secure system to communicate. And the other, of course, was the basis of communication related to how you can communicate without error. And then the third paper came in where he said, okay, they asked him, can you write something on what you think is going to be the future? And this is what he wrote about the future. He thought in 1948 that the future was machines. Machines for designing filters and equalizers. So we don't need you guys to do it. The machine can automatically design in a very efficient manner, things we're looking in our industry today to do it. Machines for designing relay and switching circuits, machines for doing what we call routing, intelligent routing on their own, and until orchestrating a melody, logical deduction. So why did Shannon at that time, who foresaw that, didn't continue? Well, the big problem was basically the computing power, and he says it would be weak in a playing skill because it is only seeing 3 moves deep. So the notion of deep was there. You have to compute what we call this backpropagation. You have to do it, basically, okay? But the problem that he saw is that a human, compared in 1948, was much more efficient because he thought that a world champion, and I hope there are world champions in this university, has basically 15 to 20 moves deep that he can compute, okay? Whereas at that time, a machine would be too long, it would take it too much time. So of course, what changed with Shannon is these 3 things. Why today we can? Because things have been able to clusterize the same thing, and we have a magic where we have 3 components which are magically combined at the same time. We have today very strong algorithms, although I told you the algorithms we have cannot generalize. They have all these problems of retraining, stuff like that. We have something which is extremely important. It's called the computing power, okay? And I'll talk about it. That will be the case of my talk, because Huawei today is heavily implicated in providing computing capability to all the community. And the third one is, of course, the massive amount of data which is available today and on which we can play. And the combination of these 3 are extremely important to have what I call successful AI. Now, of course, I'll jump on this. You have to know that our industry is now playing with a lot of AI to improve the performance. We are today, I'll jump on these slides, trying to build what we call self-learning networks. So what is a self-learning networks? It means that when you deploy a network, at the beginning the performance is not so good. With the data you gather, the antenna learns how to beam, how to tilt, and it starts improving. And after 6 months, 8 months, 9 months, the performance in terms of coverage starts to be better, better, better. It's called self-organized networks. The whole parameter starts to self-organize. It's like the car, level 5. We're far from it, but we're all working intensively today to build up basically the future of AI-based SON networks, which are able to build it up. How you do it is still open. We have a lot of challenges in terms of algorithms to be able to do this magic of you deploy and automatically it self-configures, knows exactly how to do things, okay? Let me now go back now to the main, I would say, discipline that my lab and in general a lot of labs of Huawei are working on. So, I am a specialist of a theory related to called random matrix theory, okay, which has an extension, or I'd say, with free property theory. I will not talk today about it. Why I'm saying this? Because I'm not a specialist of AI, at least 3 years ago. I got into the discipline of AI like many people today, meaning that we have different people working on AI. They can come from the computer science community, they can come from the signal processing community, they can come from the pure math community, they can come from the statistical physics community. Today, what's good about this discipline is that we have a breadth of talents, all trying to solve the problem and tackling it from a different way. Why I'm saying this? Because 3 years ago, when I was asked to work around these techniques, I was quite skeptical. Why I was skeptical? For a simple reason, I learned communication by heart, and in communication we were able to design systems without AI. Why? Because the communication engineer has very good models. Okay, everybody? And one of the famous models is the model of Shannon, which tells you that to communicate, you separate the source. You separate, of course, the channel code. You have a receiver and you can build up. And based on the models of propagation that you have today, we were able to succeed in communication. I plot here the spectral efficiency versus the capacity of different systems going from 2G, 3G, 4G, and now 5G without any problem. So when people tell me to work on that, I said there's an issue. I don't understand why. Why we would need it? Because we're very good in modeling. We do models every day, and then we implement those models. Same thing for learning. People came to me, they told me, yeah, but you don't learn with communication. I said, no, but there's a famous guy called Wiener, okay, who built up all the philosophy of how to learn, basically, and it's the basics of control theory, by the way. In control theory, when you don't have a model, well, what you do through a process called feedback, you will try to shape the input so that you target the output. And what's good about also the approach of Wiener is that we are able to also prove things much better than what we would do in AI techniques. What I mean by proof, you can showcase convergence. So if they ask you to maximize some kind of utility, well, basically you can build up the system in terms of design so that you can optimize that utility. So of course, if the utility has convex properties, it's solved. If it's not convex properties, then as a trick of mathematician, you will try to convexify it. How you convexify in mathematics, you take some kind of expectation, expected utility. Because when you do an expectation, you try to convexify your function, and then you can prove that on average your result is good. Okay, and then of course you can play with that. And this is very nice techniques that we know. Of course it changes the problem, because your strategy in transmission, instead of saying I will transmit with power P and power P1 and P2, you will say I will transmit with a probability of power P1 and a probability of power P2. And then my average rate is pi 1, the probability with power P1, plus pi 2, and you're going to build a system like this. So we have these things, okay? And you have to know that also all the people working in control, in signal processing, have been playing with all these things without the notion of deep inside. There's no notion of deep inside. It's just a process of feedback. By the way, in communication, we do this. A Wi-Fi box today, when you transmit, if the packet is not successful, you have a system called a Nacht, an acknowledgement that says it didn't pass. With the Nacht, you reduce your rate. You transmit, it doesn't work. You come back, you reduce your rate. And you go on like this. And how do you reduce your rate? You can reduce it with either the power or the error correcting code or the modulation. So we have this system which are built today, okay? So there's no reason to reinvent the wheel. So why did I get into it? Well, because of a problem that I thought was unsolvable, but came up to be solvable. So what is this problem? The only thing I want you to understand is something called VoLTE. So what is VoLTE? It's a bit of a jargon term, but you will need to learn it if you go on within our company. It's called voice over LTE. So LTE, what it means is the technology behind 4G. Clear for everybody? So in 4G, the guys who built 4G, I was one of them, the requirement of 4G was to provide mobile internet. Basically to provide a wireless ADSL experience with mobility. You have like ADSL at home, you have it outdoor. That was the requirement of 4G. We were successful in building it. Clear for everybody? But the day we started to sell the phones, some customers were complaining. Why they were complaining? Because basically they said, when I make a call, it's worse than 2G. But we said it's normal because 4G is not meant to make calls. 4G is meant to make mobile internet. So in 4G, voice is not a technology, it's an application. It's voice over IP. And the voice over IP of 4G is called voice over LTE. It's voice over IP very tailored to 4G. Clear for everybody? So of course people were complaining, and we built the system, and whatever voice over IP system you do, it doesn't work as good as 2G. Because 2G is a technology, it's tailored, that was for voice. Clear for everybody? And so you have to know, until today, many of the people who have phones, you guys, whenever you make a call, your system has what we call a CS fallback, circuit switch fallback. You go into 2G, 3G to make a call, and you surf on 4G. Clear for everybody? Today this is how it works. So of course for operators it's very bad. Why? Because an operator tells you, I'm 4G, but I need still to keep my legacy system, which is 2G, 3G. I would like to shut down, guys, because I want to refarm the spectrum. I want to reuse it for 5G, and you're telling me that I need to keep 2G. So they've been pushing us many years to make voice over LTE work. Now, why it doesn't work. I spent 2 years with my guys trying to work models. Because voice over LTE is typically an end-to-end problem. Even if I improve the coverage, you have many bars on your phone, it doesn't mean that voice over LTE or voice over IP was going to be good, because it's a packet-based. It depends on where the servers are, it goes to the base station. So even if the signal is good, you don't have a good quality. Whereas in communication, we knew that when the signal is good, it's great. That's what I need to build. When I send radio engineers on the field, they just need to ensure by taking a truck that the signal is good. They do measurements and they say, oh, the deployment is great. Stop it. We go on. Here we have something which is related to end-to-end. There's a latency factor that we cannot control. And so we spent 2 years, no success. The year where things were improved is when I talked and got with colleagues of the company, and they told me, well, we solved it. And I said, it's impossible that you solved it. We are guys good in mathematics and models. How can you solve it? It's impossible that you solved it. They said, in fact, we had a lot of measurements in different networks of different configuration with voice over LTE measures. Clear for everybody? And then what we did, well, we used AI. We did interpolation for the new voice over LTE. We tried to do some reverse engineering to find what is the new interpolation of the position of the base station which improves. And by doing that, we deployed in many places and looked at the performance. And today, by using these techniques, I'm taking off edge throughput, you have, this is in Ankara, you have factors of up to 60%, 50% improvement by using these brute force techniques with respect to very sophisticated people. And I said to myself, now I understand where we could use these techniques. There's many cases where we are lacked. It's when models are expensive to obtain, and this is a lot of cases, when the end-to-end objective function is not well defined, and when you have a high dimensional space with many parameters on which you're stuck, and there you have some improvements to do. Today in our company, you have to know that we have shifted a lot of work where instead of using classical algorithms, we have shifted to more AI algorithms across the whole chain. Where instead of using the link as the performance, we use the data. Instead of doing it manually things, we do automatically things. Instead of looking at local aspects, we look directly at the end-to-end aspect. And instead of tuning parameters, we just set the targets and things run. And today, depending on where you work in the company, either you are more physical layer, very linked to the hardware, signal processing, or you're going more at the management layer. You have different types of algorithms which are used to improve the performance of a network. And those goes from reinforcement learning, dynamic optimization, association rule mining, to graphic algorithms, transfer learning, reinforcement deep learning, and other cases on which we build algorithms to improve our system. Okay, now a couple of things which I think are extremely important for you guys to understand. Something that rapidly came up in our company is basically where to compute AI. So you have to know that the network is this, meaning that you have a base station and you have terminals. Clear for everybody? You have a two entity. Now, the majority of cases which are built today is that the devices send back the data to the network. And you do this. And then you have what we call a system called Cloud AI, which gathers all the data, and there you start crashing your algorithms on a very centralized database. We rapidly realized, and I think we were able to do it because we are one of the only providers which is not linked to one side. We don't do just phones, we don't do just network, we do the whole thing. And we realized that in many cases, you cannot do these things. What I mean by that is that in some cases, when you don't have coverage, your phone has to continue to be smart. Clear for everybody? You don't have coverage. Your phone cannot become stupid at one moment because you don't have coverage. You have cases of latency. By the way, a car is a terminal for us. Okay, a phone is a terminal, but everything is, I'm putting here a terminal, but it's much larger. In the car business, you cannot bring back the decision to the cloud and things. Things have to be done locally. A third thing also that matters quite rapidly is privacy. Many people do not want to have their data going out from here. They would like that you do AI directly on the phone. So the question arises rapidly, is it possible to build up something that does AI depending on the situation? So we built up a strategy called mobile AI, which is what we call cloud AI and on-device AI. being able to do both on both sides, okay? Of course, there are reasons why you would do one or the other, and I'll explain what's the challenges of doing it. And this is what we're working hard today, and this is also where we need your help. Okay, so for that, of course, we build up a whole portfolio, I'll jump on this rapidly, of chipsets, which today are capable, and you see here, you have different, of course, processing power. You go from teraflops to teraflops, operation per second, to something like more mega ops. And this depends on the different earphone, smartphone, laptop, PC. And we have a whole, I would say, range of chipset going from the Aston 910. They are available today, and you can use them, to something which is more the Aston 310, which can do inference or training directly on the phone. Okay? So, of course, doing this is not an easy task. Because one of the first things you can ask yourself is that when I built up a training and inference neural network on a device which has not a lot of power, I need to do some low complex algorithms. Clear for everybody? Very low complex. So for example, one of the hard things that you do, I don't have time to talk about it, when you do training on a neural network is an algorithm called gradient descent. You need to do gradient descent. Gradient descent is optimization, okay? Now the question is that once you narrow down your precision of your neural network to only binary, it becomes what we call a binary neural network. Imagine I ask you, can you implement a gradient descent on which you can only do operations which are 0 and 1? So it means that can you implement a derivative where you can only do 0 and 1? It's not possible to do that. So you need to reformulate the problem and say, how can I do a gradient descent or an optimization or a training algorithm with only binary? So when you do training, it's optimization, and you ask yourself, if it's 0 and 1, well, it means that it becomes a combinatorial problem. Clear for everybody? And the question is, how can I do combinatorial optimization? And you guys are expert of that, because then there's a big range of combinatorial problem to do what we call low precision AI. So typically an example that I give you here is a fundamental mathematical problem for us. It's a hardware, of course, implication, but the idea is, can you design a system which does a whole neural network architecture training only in binary? Okay, and when you have only binary operation. Of course, the people who have been doing disciplines in communication, they have these constraints. They build up maximum likelihood, but maximum likelihood is not possible. You're not going to test everything. You need to run up into something which makes sense. But then you can ask yourself, by lowering the precision, do I need more layers? This we don't know. Do I need also more weights per layer? All these questions are totally open. We have no clue on how to solve these problems and what are the performance that you can get. These are just one example of the things that you come up with in doing these things. Now, a second thing also which is totally open for us is how you exploit today this capability. Now that we provided you this capability, how you guys can construct some nice algorithms which can do what we call distributed AI. I'll give you an example. Imagine that you're stuck with the constraints where the data cannot go, but you need to do some kind of learning which is basically across all the people, but without exchanging the data. What would you do? One way of doing it is to learn with the data that you have. You extract from the data the model. Clear for everybody? The models are the weights that you generated. You took those weights, you send them to the phone nearby, and then the phone nearby starts the neural network by initializing its parameters on exactly what was done on the phone there, instead of randomly. You improve the weights, you improve the algorithm, and then you send it to your neighbor, your neighbor, your neighbor, and by doing a round-robin technique, you can do some federated learning. These are examples that you can do. Second example, I learn locally, I learn locally, I learn locally, I learn locally. I extract the weights, I send those weights to the base station. The base station generates a meta model based on that model. Then it broadcasts the model to all the devices. And then from time to time, they resynchronize with the improvement they did. Many, many opening things that you can do, and things become, depending on the constraints you have of the amount of data that you can pass, on the latency that you have, on the energy processing, on the different cases today. Typically, I'll give you an example, very concrete. A long time ago, when we didn't have these pervasive AI, to take a picture, how do you do? So to improve the picture camera, you have two ways. One way, of course, is, and we're working on that, is to increase the number of cameras. And today on our phones, you have up to 4 cameras. The other, of course, is all the tuning parameters that you need to take with a good picture. In general, you're not good at that because basically you don't know how to zoom, you move, you're not a photograph. So how do you do that? It's easy. You take the photo and then you send the photo to the cloud. And then we have a database of beautiful photos made by specialists. So when you take a bald guy, we send the photo to this database. We learned what is a beautiful bald, okay? And then we know that for that beautiful bald, these are the parameters. We send them to the phone and then we parameterize. This, of course, you can do it if you have coverage. Okay, and this has been implemented by many to improve the rendering of the photo. And this is why the zoom automatically, everything is great. You say, wow, I took a great picture, but we have such a learning experience with all the database. The other is to do it directly on the phone with all the processes that I give you right now in terms of IDs and how you can conduct these things. So of course, on a very simple things, we still have no clue on how to build up architectures like this, because today you have, for your information, the capability of doing pervasive AI, meaning AI nearly at any point. And the question is, of course, how you start implementing things like that. To give you an example that my colleagues in Munich did, and by the way, I strongly encourage you to do something like this. So my colleagues in Munich decided to use basically the AI capability that you had on the phone to do this experiment. It's an experiment, by the way, that you can do. That you could do. What I mean by that is that today you can pilot a car with the phone, meaning the capability of AI processing that you have on a phone is so great that you can today be able to guide a thing. So the idea was basically to showcase, I don't think you're hearing the sound, it's unfortunate, but the idea was basically to be able to drive a Porsche with a phone which could recognize on the street an obstacle and move. It means that for you guys, for your students, you could do this. What it means, you go to the supermarket today, maybe not the supermarket, but a store, you buy a small remote control car, or a small drone, but let's do a remote control car. That remote control car in general has some remote a way of moving the car. It's a Bluetooth connection. You take off the remote control, you take your phone, and you do the interface to move the car. And then what you take the phone and you put it on the car. Clear, everybody? And then you go in your lab and you draw a street to make the learning process of how to drive. And then the exam is, I give you a new pattern, show me that the car can drive. Clear for everybody? And you just have to put the phone on that. It doesn't cost you. It's mostly, roughly maybe $100, all in all, on which you can put students in a competition on working on this. Okay, this just gives you ideas of the capability that you have today on a classical phone. Okay, just to tell you that, of course, the next step that we're seeing after the example that I showed you is collaborative AI. Today we are more on this issue of distributed, and of course the next step is, of course, the rise of the machine, robots, talking together, all these things that you're seeing, and this is what we call collaborative AI. It will happen when, we don't know, but today we're giving the capability for a lot of smart people to build up their industries working on these things, okay? I'll stop here, I think, because do I still have time or not? Okay, if I have time, I can talk about some open problems which we think are challenging, and on which we think you have guys to work on, okay? I'll go rapidly because it would take me a lot of time, but I'll just jump rapidly. One of the open problem is how to merge model-based and data-driven approaches. This is total open. You have to know that today we have models, and one of the things that people do is that when they have models but they're not perfect, they take them out and go to data-driven approaches. The question is that we have models, we have data. We don't know how to merge both, okay? How people do for your information today, well, I'll just jump on this slide here. Well, they do the following, which we don't think is the best, and we think you can improve it. What they do is that they have models of some things. They're not perfect. What they will do is, from that model, mathematics, equations, they will generate data, okay, for everybody? And once they generate the data, they will translate it into a neural network. Clear for everybody? They will do learning on that synthetic data which is generated by the model. And then they will initialize the neural network to train on the real data based on the model because they already have good things. But this supposes that the model is not far off from reality. Clear for everybody? Otherwise, it's useless. This is the way we do today. We don't think it's good. We think you need to input some priors that you have directly on those neural networks in a more sophisticated manner. Okay? And this is totally open today on how we bridge the gap, because you have to know that many disciplines, physics, chemistry, us, we have a legacy of years of knowledge. We need to bring that legacy with the new data approaches which are coming. Today, we don't do this. In medicine, kick off all the data, all the experience of how doctors know, and start with scratch and learning on the data of the patients. We know things, we don't know how to merge this, okay? I'll jump on this. This was just to give you an example that today works. Second is basically Shannon. How can you build up new systems which basically solve the second case of Shannon? So in the book of Weaver and Shannon, there was two things. There's level 1 communication, which is basically how to transmit data without error. There's level 2 communication, it's called semantic communication. How can you ensure that the meaning of your information has been understood, basically? It requires that you embed some kind of semantic in your communication, okay? And basically what's the idea is that when you start communicating with people, this is true, the more I communicate with you, the less I will need to communicate in the future. I don't know if I'm clear, because the more I communicate, we start building some kind of context between us. And therefore, I don't need to transmit you much more because you already understand the way I think. Okay? And we think that the second level of communication called semantic communication will play an important role. You have to know that there's semantic computing, semantic communication, and many things. The semantic are techniques which are based on these AI techniques, but we still don't know how to build them up. This is another problem. I'll jump because I don't have time to explain details how to do. The third one is basically this pervasive AI in terms of understanding. We have no clue if we provide intelligence everywhere, how the system will behave. Clear for everybody? How will converge? We have no clue. We're providing converge. I'll give you an example, for simple things. You have to know that in game theory, which is another field, when you suppose that you have distributed decisions, but you suppose that these are based on rational decisions, so there's a concept of rationality. We are able to prove basically a Nash equilibrium, so the system will converge, which is already good with some conditions that we put. And second, we're also able to tell you what is the gap between a total centralized system with a distributed system. It's called the price of anarchy. And for example, many mathematicians have work showcasing that if your utility function is linear, it's a polynomial of degree 2, of degree 4, and you go on like that, the price of anarchy is bounded by 4/3, things like that. What it means that a distributed system with respect to a centralized system, you have a loss of 1/3 of performance, which means that if the overhead of communication is more than 1/3, clear for everybody, it's better to go to decentralized because there's a cost in terms of centralizing, okay? We don't know. You have to know that some people are today working on a field called mean field game theory, which tries to analyze basically when you have intelligence, which is distributed, and this is what we're doing, with each one having a DNN implemented, how the system will behave. For example, one of the founders of the mean field game theory without machine learning, but today they're merging, is a guy called Pierre-Louis Lyon, who's a mathematician, a middle field also. And one of the good things of Pierre-Louis Lyon is that they've been able to explain, but not for our case, we're trying to work closely with him, by the way, the Ola in a stadium. I don't know if you know what is Ola. Ola, so in a stadium, for some reason, people start waking up, and there's like a big thing in the stadium happening, okay? And one of the questions that was asked to him is, can you give us the speed at which it goes, and on which direction it goes? And in fact, it's an optimal control problem. You say that Z is your altitude, T is the time, and X is your position in the stadium. Clear for everybody? you have a big tendency to mimic your neighbor. And the coefficient 2 is the learning that you will do, because you have a lot of data. It can be square, it can be a function of that. But it's a distance related. So in general, when you're a stadium, you mimic your neighbor. And then there's a cost function. It costs you in general to be like this rather than sitting down. Clear for everybody? And then there's also a cost related to the speed at which you move, if you go faster. So if you integrate this function and you try to find the z, which is the wave in a stadium, which optimizes the mimicking behavior, which is basically how you start looking at your neighbor. With respect to this cost function, you get exactly the things like that. And we're able to explain a lot of phenomenon like that related to what's the optimal placement of a towel in a beach. Ask yourself, where would you put your towel on the beach? What's the optimal placement? Many factors. In general, depending on your behavior, you don't want to get too much crazy with the people because they're too crowded. But then it depends also where the toilets are. And so you can also find exactly the optimal placement by these techniques, which are quite sophisticated, but also quite nice to do it. Last point on which we have no clue is what I call learning, or this generalized AI. And this is something also we have a couple of scientists in my company and in my group also trying to work on this. And I told you today, what's missing is basically the logic that you can embed in the data. We need to extract the rules on top of exactly just the conclusions that you get. How can you embed logic on the data? This is extremely complicated problem. Today, of course, we have no clue how to do it. The way people are trying to solve it, I'll jump on these things, is to use what we call category theory. One of the big schools of category theory is Laurent Laforgue in France, but there are also people working on topos like Grothendieck and many others working on these things. And today we're trying to build up these techniques to be able to at least go beyond the classical learning. So it's not an easy task. We have a paper, by the way, on this topos perspective that we have started to write with some colleagues. But I strongly encourage you also to look at that. We have no clue. It's totally open on the approaches. Okay. Finally, a guy asked me before, in our company, we do have a couple of deep problems that we would like mathematicians to solve. These are the type of problems that today we have to solve. For example, how you do spatial computing, neural symbolic computing, geometric mapping of depth models, the correlative computing, high precision model and low precision model equivalence theory from low precision to high precision DNN. I can give you a more detailed, of course, explanation of these things. We have also here, as you see, information bottleneck theory, network optimization, efficient optimal transport. Optimal transport is being used. Distributed AI, a unified learning framework for distributed AI, safe and trustworthy AI. We have scientists who are working on these problems, and I can give you, of course, the slides will be available, by the way, and we have also some small description of each of the problems that we would like also the community, because we think that whatever you solve, even if it's not good it's not immediately for us, it's okay, in the sense that we would like that to know where the industry should go. Okay? I'll stop here and respond to all your questions.
Let's have the speaker. Any questions or comments?
Yes.
Okay, so you mentioned that devices may share their learning results between each other. But if some device will get spoiled data, won't it propagate it to others?
That's a good question. This is why today we don't hop. The idea is that you take the weights and you send them. It's totally right. We still don't have an understanding to provide a completely decentralized decision in a network. We don't do decentralized at the moment. This is one of the things we would like to see happening and understand, but we don't do this today. Sorry. Yeah. We don't do this today because we don't have an understanding of. Imagine that you have different terminals with different capability of learning, basically. That's the first thing. Second is also all these problems of noisy, I would say, exchanges, which is also a problem because when you start learning on noisy data and you start not initializing, and all these things are open. We would like to understand. This is why one of the problems I showcased here is exactly what is a unified learning framework for distributed AI. This is an open topic for us. Did I answer your question? Yeah.
Any other questions
Yeah.
or comments?
Thank you for your presentation. And my question is about some model optimization techniques. Thank you for your presentation. And my question is about some model optimization techniques like pruning, distillation training, and some other. What do you think? What technique is the best, or maybe some?
So at the moment, each one has its advantages and drawbacks. For example, in this approach of information bottleneck, which uses distillation, by the way, we thought that it could solve the problems, but then we realized that it's highly dependent on what we call the activation functions. If you use ReLU or something, so I don't know if you're familiar with that, but you have non-linearities in these activation functions, and this changes also the problem. So there's many things that we don't have a full clue on how they're working, and this is why it's quite dependent on technique, and then each one has its drawbacks. So everybody thought, by the way, that this was the big thing for explaining AI, and then realized no, because it was only for a specific case that this CB solved it, and now we're trying to understand better. Yeah.
Thank you, guys.
Any other questions or comments?
Yeah, a question and a question there.
Thank you for presentation, and I have a question about morality. And for example,
About
morality question.
morality.
Yes.
Okay.
So in your example, if we want to have a beautiful picture and we change it some way, so it may appear a problem that, for example, this photo cannot be an evidence in some charge case or something like that, or for example about machines that can find whether patients have cancer or don't. So if the machine said that the patient does, so what do we have to say to the patient, because we have no clue how the machine works.
Okay, so we don't talk about moral. I mean, the term morality that you're saying is built up in here. It's called safe and trustworthy, meaning you can trust the result. So this is how we call it. We don't call it morality, but this is a big issue for us, for sure, in the sense that not only in our industry, and this is why you put many people, is to build up the confidence on the conclusions that we got, and we can ensure how the result was obtained. Because all these problems, even if you say that you would like to use this photo as a case, there is no issue as long as we know how we got the result. You understand what I'm saying? Because then we can always explain that this photo, this is what has been changed and how it was changed. Today, unfortunately, this is still an open topic. It's related to opening the black box to be able to understand how things. And it's not only our industry. Today, if you decide to work in the banking industry, the bankers, at least the banks, are pushing guys like you to tell them why somebody did not get a loan. You understand what I'm saying? Because basically what we do today is we take all your information, we put it in the machine, and the conclusion is that we don't give him a loan. That's the conclusion of the machine. But then of course you as a customer, you want to go back to your bank and say, but why didn't you give me a loan? Today we cannot explain you why we don't give you a loan. Because we ran a lot of data based on you, your parents, your connection, and this is the conclusion that they had. So it's a big topic today to be able to explain AI. It's called explainable AI. And my answer today is that we need smart people like you to solve this today. We don't know. Okay?
Okay, I think that, well, a lot of your questions, but our speaker will be accessible after the lecture. What I suggest is to sum him right now. So let's send the speaker again.